Welcome to this lecture on fundamentals of transport processes. Previous 3 lectures I gave you some insight into dimensional analysis. I am sure most of you have done dimensional analysis before, but the objective of the previous 2 lectures was to give some physical meaning to those dimensionless groups that we get when we do dimensional analysis. So, now it is time to turn to how we are going to analyze transport processes in this course. Previously, when we looked at transport processes, we considered an equipment as a whole. For example, in our initial lecture on the flow through a continuous reactor, we looked at the reactor as a whole, and we looked at what comes in, what goes out, and tried to write some balances for the fluxes that go through reactants to the surface of the reactor, fluxes of products out, and fluxes of heat either in or out. When we looked at the heat transfer problem, we were writing an equation for an average heat transfer rate or an average heat flux across the entire heat exchanger as a function of the average temperature difference between the inside and the outside. Similarly, when we were looking at the spray dryer problem, we were writing the mass transfer, mass flux and the heat flux from the surface to the gas as a function of the average difference in concentration between the particle surface and the hot air, or the average temperature difference between the particle surface and the hot air. So, in that sense, we got correlations for various situations. Okay. For example, we got correlations for the flow in a pipe. The Reynolds number, the friction factor is a function of Reynolds number, and this was the average stress that is acting on the surface of the wall of the pipe, the pressure drop that is required to drive the flow. This was not the microscopic stress at every point within the fluid. Okay. So, in this course, we are going to look at microscopically what causes transport of mass, momentum and energy locally at specific locations. So, we are going to make a couple of simplifications. First thing, we are not going to analyze an entire equipment, an entire reactor, an entire heat exchanger. Rather, we are going to focus on the locations that are important for the transport process to occur. So, for example, in the case of the catalyst pellet, we would like to find out what is the flux from the fluid to the surface. Okay. Of course, it is going to depend upon the average concentration difference between the bulk concentration and the surface concentration of the material. But the bulk concentration is not a constant. Obviously, as you come closer and closer, the bulk concentration, the concentration within the fluid has to approach the surface concentration. In a similar manner for the heat transfer problem. Okay. The heat that is transferred either into or outside the catalyst surface is going to depend upon the difference in temperature between the surface and the bulk. Of course, the temperature is not going to be a constant throughout the fluid. As you come nearer and nearer to the surface, if the catalyst particle is hotter, the temperature is going to be larger at the surface than at in the bulk. So, how do these variations give rise to these fluxes? Similarly, in the case of the heat exchanger problem, we plotted the average heat transfer rate as a function of the average difference between the wall temperature and the average fluid temperature. Okay. The fluid temperature, of course, is a function of location within the heat exchanger. For example, if the fluid is hotter than the wall, then the temperature is going to be large at the center of the heat exchanger, and it is going to decrease and reach the wall temperature at the wall. Okay. And when you do empirical correlations, this variation is all approximated as just one constant temperature. Okay. In this course, we want to find out what is the temperature variation itself. That involves 2 things. One, necessarily the configurations that we analyze will be much simpler. We will take either the flow through a tube, the flow past some flat plate, okay, where you have some velocity profile near the flat plate. Okay. And we will try to find out the dependence of the temperature with height away from the surface, as well as how it varies along the plate. Okay. And of course, the flux can be determined from the variation of temperature near the surface using the using the Fourier's law for heat conduction. Similarly, for the catalyst surface, we will try to calculate the temperature field everywhere around the catalyst surface. Okay. We will not just try to approximate it as a one constant in one location, another constant in another location, but rather we want to actually evaluate how that temperature varies as a function of location as you move closer and closer to the catalyst surface. Okay. So, because of that, our description will necessarily be simpler. We will not consider the large equipment that we have been considering before, but rather we will just consider what happens locally at the catalyst surface, near the wall of the tube, near the wall of a flat plate, and so on. Okay. So, first things first, okay. In this course we will be dealing primarily with fluids. Now, materials can be classified broadly into two types. One is fluids and solids. Okay. Okay. So, mechanically the difference between a fluid and a solid is that if I take a block of a solid, okay, and I apply a stress or a force along the surface, that solid will deform for a little bit and then it will stop. Okay. So, it will deform a little and then it will stop, because the solid creates a resistive force that resists the force of deformation that is applied on the solid. Okay. If the solid were perfectly rigid, then it would not deform at all. Okay. But in general, it will deform for some time and then it will stop. Of course, if you increase the stress even further, it will reach a breaking point or a yielding point where there will be failure. Okay. But if the stress is small enough, it is going to yield for some time and then it will stop. Okay. A fluid, on the other hand, if you apply a stress on a surface, is going to continuously go on flowing. Okay. So, in a solid, a stress creates a deformation. Okay. It creates a displacement of solid material points around their unstressed states. Okay. So, there is a displacement field, and this displacement field can be characterized using a strain within the solid. In a fluid, an applied stress creates a velocity field. The fluid will deform continuously as long as the stress is applied. Okay. It is not going to stop until the stress is removed from the fluid. Okay. So, solids deform and then stop. A stress causes a strain deformation in the solid. Fluids continuously deform under stresses. Stress causes a strain rate in a fluid. Okay. And you must have be recalling the Newton's law for viscosity, which says that the stress is proportional to the strain rate. Strain rate is difference in velocity divided by the distance. Okay. At the molecular level, the difference is because in a solid, all the molecules have fixed positions on a lattice. Okay. There could be different kinds of lattices. There could be hexagonal close packed lattice, there could be face centered cubic lattices, there could be body centered cubic lattices, and so on. But all of these molecules, they have fixed positions. Okay. And they vibrate a little bit around these fixed positions, but they cannot undergo large displacements about their fixed positions. Okay. So, each atom in a solid is linked by a bond to the neighboring atoms. Okay. The bond could be shared electron clouds in metals or other types of bonds in non-metallic solids, but each molecule stays in its fixed location because that is at the center of attraction of all the neighboring molecules. So, if I apply a small displacement about this location, the molecules will change a little. Okay. And the bonds between these molecules will get stretched. Okay. And because of that, there is a resistive force that is applied on the solid. Okay. This displacement of the molecules causes a stretching, which causes a force which tends to bring the molecules back to their equilibrium locations, and that effectively resists deformation. In fluids, on the other hand, the molecules do not have fixed positions. Okay. In fact, molecules in a fluid are in a state of constant thermal motion, and the thermal velocity, as you would know, is given by the equipartition of energy, square root of 3 kT by m. Okay. So, a molecule in a fluid is undergoing some random motion. Okay. It has no fixed position, but it undergoes a random motion with time. Okay. And because of that, if I apply a stress in a fluid, the molecules can rearrange themselves in such a way as to accommodate the stress that has been created. And obviously, since the molecules can diffuse around, okay, they do not have fixed locations. Therefore, if you apply a stress, the fluid will continuously deform. Okay. Important to note, this difference has implications both for mechanical properties. The fluid deforms continuously, whereas the solid deforms and then stops, but also for diffusion. Okay. The diffusivity of these molecules in the fluid gives rise to the diffusion of mass, momentum and energy, as we shall see in the next lecture. Okay. Whereas in the solid, the molecules do not diffuse apart from mechanisms such as vacancy migration and interstitial diffusion, which are very slow processes. Okay. So, this is basically the difference between fluids and solids. In this course, we will deal primarily with fluids, okay, with the exception of heat transfer, heat conduction. Heat conduction occurs by the same Fourier's law, whether it is in solids or in fluids. Okay. The mechanisms are different. In fluids, heat conduction can occur because of the physical motion of molecules. In solids, it cannot. Okay. It occurs due to the transmission of energy by the vibrational modes of solids. However, the equations for Fourier's law for heat conduction for both fluids and solids are the same. Only the thermal conductivity, the constant in that equation, changes. And therefore, for heat transfer, we will equally what we do will be equally applicable to solids as well as fluids. Okay. Fluids can further be subdivided, okay, into gases and liquids. Okay. The basic difference between gases and liquids is the distance between the molecules in gases and liquids. Okay. In gases, the molecular distance is much larger than the molecular diameter. Okay. It could be typically 10 to 100 times larger than the molecular diameter. Okay. So, in gases, the molecules actually meet through rare interaction events which are called collisions in kinetic theory of gases. Molecules move large distances between successive interactions between neighboring molecules. Okay. And because they move large distances, the mean free path, the distance between successive collisions, is large compared to the molecular size. In liquids, on the other hand, the distance between molecules is comparable to the molecular size. Each molecule in the liquid is sitting in or close to the potential well of attraction of the neighboring molecules in the liquid. Okay. So, because of that, the molecules are frequently in interaction with all their neighboring molecules, and they do exhibit diffusion. Okay. But however, that is a slow process, because for one molecule to diffuse in a liquid, it is necessary that other molecules have to move out of the way. Okay. So, for example, if one molecule has to move this way, other molecules have to move out of the way, okay, before diffusion can take place. So, molecular diffusion is a slow process in liquids, it is a faster process in gases. Okay. In the case of gases, as we shall see, the diffusion mechanism is the same. Okay. Since the molecules are not in continuous contact with each other, transport of mass, momentum, energy has to take place due to the physical motion of the molecules themselves. In liquids, that is not true. The molecules are very close to each other, and so you do not require the transport of molecules to have the transport of momentum or energy. Mass transfer, of course, requires the transfer of molecules. Okay. Despite this significant difference in the density between liquids and gases, because the molecular diameter in gases is about 10 times, because the mean free path in gases is about 10 times the molecular diameter, and the mean free path in liquids, or the distance between molecules in liquids, is comparable to the molecular diameter. The density of gases is approximately 1,000 times less than the density of liquids. For example, water has a density of about 1,000 kilogram per meter cubed, 1 gram per centimeter. On the other hand, gases, air typically has a density of about 1 kilogram per meter cubed or thereabouts. Despite this difference, the fundamental equations for diffusion end up being the same in both liquids and gases. In both cases, mass transfer, the flux of mass is related to the concentration gradient by the Fick's law. In both cases, the flux of energy is related to the temperature gradient by the Fourier's law. In both cases, the stress is related to the strain rate by Newton's law of viscosity. Because these laws are the same, the analysis that we carry out for liquids and gases will be the same. The laws are the same, the coefficients in those laws change. The coefficient of viscosity is going to be different for liquids and gases. Coefficient of thermal conductivity will be different in liquids and gases, and similarly the coefficient of mass diffusion will be different in liquids and gases. But the relationships between the fluxes and the gradients in the densities of those of the quantity which is being transported, those relations are the same, and so we will be able to treat both of these using the same relationships. In this course, we will make no distinction between whether the substance is a liquid or a gas. The equations that we derive will be the same for both. The only difference is that the coefficients in those equations will change when one goes from a liquid to a gas. Okay. Next, what is the description that we will use? Okay. So, I said we will analyze simple situations such as the transport around a catalyst pellet or a spherical droplet, the transfer across the surface of a pipe and other conduits across a flat plate and so on. Okay. So, let us assume that have a catalyst pellet here. Okay. And we were looking at the heat conduction problem. The surface of the catalyst pellet had a temperature Ts, and the temperature far away was some other temperature T infinity. Okay. Of course, as you approach closer and closer, temperature is going to go from T infinity to Ts. Okay. And similarly, if I were doing a mass diffusion problem, the concentration would go from C infinity to Cs. Okay. So, in this course, we will use a continuum description where we define a coordinate system. Okay. The way that I have written it, the coordinate x is coming out of the screen towards you, and y and z are in the plane. Okay. So, this is a 3-dimensional coordinate system. Okay. And we will define temperature field a temperature field as a continuously varying function throughout the domain. Okay. We will define a temperature field as a continuously varying function throughout the domain. Okay. So, we define T as a function of x, y and z. Okay. Similarly, if I were doing a mass diffusion problem, I will have a similar situation, except that at the surface I will have some surface concentration, and far away I will have concentration C infinity. Okay. But once again I would define a concentration field. Okay, C of x, y and z. Okay. And similarly, for a momentum transfer problem, for example, if I had flow through a pipe, for example, I would define a coordinate system z, x, y. Okay. And here I would define the density fields, density field as the total density, mass per unit volume, rho of x, y, z, and the velocity field. Okay. Velocity field, velocity can be in 3 different directions. In this particular problem, if the flow is unidirectional, I will have only one component of the velocity along the z direction. In this particular problem, the flow is unidirectional. So, I will have only one particular component of the velocity. In general, you could have different components of the velocity. I have used here one component of the velocity for a particular reason. This component of the velocity is the velocity is in the z direction, but it could vary with respect to both the x and y directions. Okay. So, one component of the velocity can vary with respect to all three coordinates. Okay. So, density is a function of x, y and z, and each component of the velocity is also a function of x, y and z. Okay. A function, first thing, it is a single valued function. That means that at a single point in space you can have only one value for that function. So, at a fixed point in space you can have only one value for the temperature, one value for the concentration, one value for the density, one value for the velocity. Okay. So, that is the meaning of a function. Secondly, the function has to be smooth in the sense that the function has to be continuous and its derivatives have to exist. Okay. So, a function that is smooth can be any function. Okay. A function that is discontinuous will have one location at which it has multiple values. Okay. There is a discontinuous transition in the value of the function at one particular location. Okay. A function could be continuous, but its derivative could have two values. Okay. So, for example, in the case of the blue curve, as I approach this point from the left, I get one particular slope. As I approach it from the right, I get a different slope. Okay. So, the derivative is discontinuous at this point. Okay. In the present course, all of these functions will be continuous functions and differentiable. That means their derivatives also exist. Okay. So, they are smooth functions, single valued functions throughout the domain. Physically, what is the meaning of this field, this function? Okay. First of all, it is varying continuously along the x, y and z directions. Okay. So, we have a picture where we are describing the temperature, the density, the concentration by these functions which are varying continuously in all three directions. Okay. But a real fluid has molecules in it. Okay. So, it is not just a continuous function, it actually has molecules which fluctuate about, okay, and the density within a control volume is the number of molecules in that volume divided by that volume itself. Okay. So, how do I define the density field? Okay. At a point, okay, if I wanted the density at location x, y, z, okay, I construct a small volume okay, around this location x, y and z. Okay, around this point x, y and z, I construct a small volume delta V, okay, and I find out how many molecules are within this volume delta V. Okay. So, the total mass within delta V is equal to the number of molecules times the molecular mass. Okay. Where n is the number of molecules and m is the mass of one molecule. So, the density is defined as the number of molecules times the mass of a molecule, total mass within this volume divided by the volume delta V itself. Okay. This is for a small volume. So, this is in the limit as delta V equals to 0. So, formally this is the definition locally of the density. Okay. So, I take one particular location x, y and z, construct a small volume around it, find out the number of molecules in that volume, and as I shrink that volume, make it smaller and smaller, I measure the mass within that volume divided by the volume itself. In the limit as the volume goes to 0, the number of molecules and the mass of the molecule, the total mass will go to 0, the volume will go to 0, but the ratio will not go to 0, it will go to some constant value which is only a function of that location. It is not a function of the size of the volume in the limit as the size of that volume goes to 0. Okay. So, that is the formal definition of the density. Okay. clearly there is a problem with this definition. Okay. As I make my volume smaller and smaller, okay, if I had a significantly large volume, I would have many molecules in it. But as I make it smaller and smaller, I might have just a few. Okay. And these molecules are in constant random motion. Okay. So, they may come into the volume, they may go out of the volume. Okay. So, if I take this measure of density and look at the density as a function of time, okay, it is going to undergo large fluctuations. Okay. Just rub this off. Cannot go negative. So, you will undergo fluctuations in time. Okay. When a molecule is in, you will get a larger density. When a molecule is out, you will get a small density. Okay. So, obviously, this volume cannot be as small as a molecular size or even a mean free path. Okay. When you make the system larger, okay, you have a large number of molecules in here. Okay. So, there will still be fluctuations in the density, okay, but they will be much smaller. They will be much smaller because when the number of molecules is large, one molecule coming in or going out does not make that much of a difference to the total mass of the system. Okay. So, there will be fluctuations about some mean value, but those fluctuations will not be large. Okay. So, the size of those fluctuations decreases as you make this volume larger and larger compared to the molecular size. Okay. However, I cannot make this volume comparable to the catalyst particle size, because I want to find out what is the variation of the concentration over distances comparable to the radius of the particle itself. Okay. So, the volume cannot be made too large such that it becomes comparable to the macroscopic size. Similarly, in the case of the fluid flow, I cannot make the volume as large as the tube radius itself, because I want a local description. Okay. So, the volume has to be small compared to the tube radius, okay, so that I can get a local description. I can define density, concentration, temperature and so on at a given point. So, it has to be small compared to the size of the characteristic length scale of the system that we are considering. At the same time, it has to be large compared to the molecular size, otherwise you will have large fluctuations. Okay. So, what is the micro scale in this case? The molecular size in the case of liquids, or the distance between particles, the mean free path in the case of gases. In the case of liquids, we know that the diameter of, let us say, hydrogen molecule is approximately 1.38 angstroms. Okay. The diameter of oxygen is approximately 3.8 angstroms. Okay. The diameter of water is about half the diameter of an oxygen molecule. Okay. So, therefore, in the case of liquids, this size has to be large compared to this angstrom level or nanometer level molecular size. Okay. However, it has to be small compared to the macroscopic size. Okay. So, for example, if I had a catalyst pellet diameter 1 millimeter or a pipe of diameter 1 centimeter, okay, the volume that I consider has to be small compared to 1 millimeter or 1 centimeter. Okay. So, here I have a microscopic scale, okay, which is for liquids. It is about 10 power minus 9 to 10 power minus 10 meters. Okay. In the case of gases, the relevant microscopic scale is the distance between molecules, or the distance a molecule travels between successive interactions. Okay. And we will see a little later, we will actually calculate this in the next lecture. Okay. In the case of gases, this varies from 10 power minus 6 meters to 10 power minus 8 meters roughly, okay. 10 power minus 7, 10 power minus 6 meters. Okay. Whereas, the macroscopic scale is 1 millimeter, okay, which is 10 power minus 3 meters, to let us say 1 meter, which is 1 meter. Okay. So, in between this microscopic scale 10 power minus 6 to 10 power minus 8 for gases and 10 power minus 9 to 10 power minus 10 for liquids, and this macroscopic scale, we have a sufficient range of scales in such a way that we can define average quantities. Okay. So, if I plot the averaging volume, the averaging length scale for the averaging as a function of density, okay, this is about 10 power minus 10 and this is about 10 power minus 3 in meters. Okay. So, at 10 power minus 10 I will get large fluctuations because a molecule may be inside or outside. Okay. As this becomes larger, but still smaller than the macroscopic scale, the density will converge to a constant value. Then as it becomes still larger, I will start getting variations again, because I am actually averaging over real concentration variations within the system. Okay. I am actually averaging over density differences across the pipe or over length scales comparable to the radius of the catalyst particle. Okay. So, this microscopic volume is defined in such a way that it is large compared to the molecular size, but still small compared to the macroscopic scales. The definition of this requires that I have a sufficient range of sizes, sufficient range of length scales between the microscopic scale on the one side and the macroscopic scale on the other side, such that I can find scales in between, okay, which are large compared to molecular size or mean free path, but still small compared to the macroscopic scale. Okay. Over that volume I can do this definition of density. Okay. So, the volume cannot be too small, it cannot become smaller than a molecule. Okay. It has to be much larger than a molecular size, but still small compared to the macroscopic scales in the problem. Okay. If I define my volume in that range and I draw a volume around a point, count the total mass within that, divide by the volume, in the limit as this goes to 0 in comparison to the macroscopic scales, but is still large compared to the molecular scales, I will get a constant value for the density as I vary the size, so long as it is large compared to the microscopic scale, but still small compared large compared to the molecular scale, but still small compared to the microscopic scale. In this range I will get a constant value that is defined as the density at that particular location in the continuum approximation. Okay. So, that is the physical meaning of the density field. Okay. At each location I draw a volume, find the mass in that volume, divide by the volume, in the limit as that volume goes to 0 compared to the macroscopic scales, but is still large compared to the molecular scales, I can define a density. If my system size is very small, if my system size is comparable to the molecular scales in nanotechnology applications, for example, in that case you cannot define a continuum density. Okay. And as we shall see in this course, once you can define continuum fields, then you can do some pretty complicated analysis with those continuum fields. If the molecular size is not small compared to the macroscopic length scales, you do not have that, and you have to consider the system as a collection of discrete particles. Okay. So, this is the definition of the density field. Okay. So, this is the location x, y, z, okay, and I construct a small volume around this location delta V. Okay. There is the volume delta V, and then I take the limit as delta V goes to 0. Okay. So, in the limit as delta V goes to 0 of number of molecules times the mass of a molecule divided by delta V is equal to the density field. Okay. How about the velocity field? Okay. So, let us just take for example the velocity in the x direction. Okay. So, in this differential volume, I have a large number of molecules and these have some fluctuating velocities to them. Okay. I can take the summation over all the molecules I is equal to 1 to n of the molecular mass times the velocity of that molecule in the x direction. Okay. So, I go over all the molecules. Each molecule has one particular velocity along the x coordinate. Okay. This is the x coordinate is coming out of the plane of the board. I take the component of the velocity along the x direction for each of these molecules. Okay. I add them all up. Okay. Add up all the x components of all the molecules within this differential volume. Okay. Divide by the volume, and I take the limit as delta v goes to 0. Okay. This is equal to the momentum density. This is the mass times the velocity, that is the momentum, okay, summed over all of the molecules divided by the volume. So, this is the momentum density. This is rho times the momentum density ux. Okay. Okay. So, this is the density times the velocity in the x coordinate, and the velocity ux is determined as rho ux divided by rho. Okay. So, the the ratio of the momentum density defined in this manner over all the molecules divided by rho is given is the velocity. Okay. If the molecules had purely fluctuating velocities, okay, they have equal probability of having velocities in the plus x direction and the minus x direction. In that case, this mean velocity in the x direction will be identically equal to 0. Okay. It is only if there is some net flow that the molecules are biased towards the velocity in one direction or the other, only then will you get a non-zero velocity ux. Okay. Similarly, one could do this for the other components of the velocity as well. Okay. I could define rho uy is equal to limit as delta v goes to 0 of summation I is equal to 1 to n of m times vy, where v is the molecular velocity. Okay. This divided by delta v. Okay. And then you could define uy is equal to this divided by the density. The density field I have already calculated over here. Okay. So, that is how you define the components of the velocity, okay, the mean velocity. Okay. Similarly, rho uz is equal to limit as delta v goes to 0 of summation of m vz by delta v. Okay. However, I do not really have to think of it in this manner. Okay. I could very well define the velocity vector itself. Okay. I could define the momentum density as the density times the velocity vector itself. Okay. So, I could define a vector momentum density, okay, u stands for a vector, okay, is equal to limit as delta v equals to 0 of summation over all molecules of mass times the velocity vector divided by delta v. Okay. For I is equal to 1 to n. Okay. So, this is a vector summation over the velocity vectors of each of the molecules. Okay. And we will see later in the course there are certain advantages to treating this as a vector itself. Of course, if you expand this out, you will get precisely the same thing that I got earlier. Okay. So, if I define u vector is equal to ux times ex plus uy ey plus uz ez, okay, where ex, ey, ez are the unit vectors, ex, ey, ez, okay, these are 3 unit vectors in the 3 coordinate directions. Okay. This is going to be equal to ex times limit as delta v goes to 0 of summation of m vx by delta v plus ey times limit plus ez. Okay, so this will be the three components of the velocity, where ux is equal to summation of mvx by delta v, uy is equal to mvy by delta v, and uz is equal to mvz by delta v. Okay. So, this is just an expansion, but I am just trying to point out that you could very well define the momentum vector itself. So, rho times u is the momentum density vector. Momentum has is a vector because it has a direction associated with it. It is just a summation of the momentum of all the particles, okay, within this control volume. Okay. So, that is how you define the momentum density field. Okay. The temperature field is a little more complicated. Temperature has to do with the fluctuating velocity of the molecules. Okay. Now, if you had a control volume, okay, in which you had, let us say, a monatomic gas, okay, so that it had only translational degrees of freedom, the total energy of fluctuations within this volume is calculated as follows. Okay. Energy of, for a single molecule, the fluctuating energy if it had only translational degrees of freedom, would be equal to m times v minus the average velocity square. Okay. This is the kinetic energy of the velocity fluctuations alone. Okay. There is the kinetic energy associated with the mean motion, okay. And then if you subtract out the kinetic energy of mean motion, you get the kinetic energy of the velocity fluctuations. Okay. So, this is the fluctuating energy of a single molecule. The fluctuating energy density is calculated by summing this over all of the molecules. Okay. Summation I is equal to 1 to n of half m into V I minus u whole square. Okay. Okay. This divided by delta v in the limit as delta v goes to 0. Okay. So, this is half m v RMS square by delta v in the limit as delta v goes to 0. Okay. This has got to be equal to, from the equipartition of energy, 3 by 2 n k T, where n is the number of molecules. Okay. So, this basically defines what is the temperature field. Okay. The temperature field is related to the energy fluctuations. Okay. If the molecules were not just monatomic molecules, but they had rotational and vibrational degrees of freedom, those energies would have to be included in here, and the number of degrees of freedom. Okay. So, this will be equal to n CV k T. Okay. Okay. I am sorry, this should be 3 by 2 m n. Yeah, I should multiply with mass. The mass of a molecule times the number of molecules is just the mass density. Okay. So, this is equal to rho CV T. Okay. Where 3 by 2 n k is the CV for the system. Okay. Yeah. Just remove the k here. Okay. Good. So, this defines the temperature field. Okay. So, now that we have defined fields which are continuously varying functions of position, now how do we work with these fields? Okay. So, basically what we are trying to do is to write down conservation equations, okay, for these fields. Okay. Basic equations, conservations of mass, momentum and energy. Okay. So, one component is going to be conservation equations. For example, for a differential volume, okay, that I take locally around a point, the mass conservation will be of the following kind. Okay. Change in mass in a time delta t is equal to mass in minus mass out. Okay. So, the change in mass in a time delta t is equal to the total mass that comes into this differential volume minus the mass that goes out over all of the surfaces, okay, the right, left, the front, back, and the side surfaces. You do not have to do it for a cubic volume, you can do it for any size volume. Okay. The change in mass within this volume is going to be equal to the net mass in minus the mass out, okay, of this differential volume. Exactly the same holds for energy. Okay. Change in energy is going to be equal to energy in minus energy out. Okay. The change in mass in a volume is going to change the concentration locally, change in energy is going to change the temperature locally. Okay. For momentum transfer, we use a slightly different form of the balance. It comes out of Newton's laws of motion. Basically, what it says is that the rate of change of momentum is going to be equal to momentum in minus momentum out plus sum of all forces acting on the body. Okay. So, these are the basic equations that we will use. Okay. Now, we have defined the temperature, the concentration, the velocity at a given location, and the change in momentum, energy or mass, okay, within that volume is going to determine the change in the temperature. Okay. However, the temperature, concentration, velocity are also changing with position. Okay. So, to find out what is the energy in and energy out, we have to know how these field variables, the temperature is changing with position, because as you know, heat flows from a higher temperature region to a lower temperature region. So, unless there is a change with position of the temperature, you are not going to have a transfer of heat. Similarly, mass goes from a region of higher concentration to lower concentration. Unless you have a change in concentration, there is going to be no transfer of mass. Okay. So, in order to complete the balance equation, you need to have some way of saying how the transfer, the flux of energy is related to the changes in temperature, how the flux of momentum is related to changes in velocity, and how the flux of mass is related to changes in concentration. Okay. And these things are what are called constitutive relations. Okay. We have already seen these constitutive relations. We saw, for example, Fick's law for diffusion across a surface, a slab of fluid. Okay, of length L with two different concentrations. Okay, J was equal to minus d delta C by L. Similarly, Fourier's law for heat conduction, similarly Newton's law for viscosity. Okay. These were written for a slice of fluid. Okay. In this particular case, we would like to apply these same constitutive relations to small volume, differential volumes in the limit as that volume goes to 0. So, these constitutive relations are going to be written locally at these positions, okay, for each differential volume. Okay. So, if I did the same thing, okay, for a volume of infinitesimal thickness in this direction, say delta y, okay, J will be equal to minus d times delta C by delta y. Okay. And as I make this thickness delta y smaller and smaller, in the limit as delta y goes to 0, I get dC by dy. Okay. So, this is the first derivative of the concentration with respect to the flux. Okay. This is the flux in the y direction. Okay. Note here, I have used a derivative with this partial sign. Okay. What does this mean? This means that I am taking the derivative with respect to y, keeping the other coordinates a constant. X is a constant, z is a constant, time t is a constant. Okay. At a given time, I go from location y to location y plus delta y, okay, keeping x and z a constant, find the variation c as I move. Okay. That difference divided by delta y is the partial derivative. Okay. It implies that x is equal to constant, z is equal to constant, and t is equal to constant. Okay. So, this is the flux in the y direction. Similarly, I could define a flux in the x direction, minus d partial c by partial x, and in the z direction. Okay. What about if I had variations in all three directions simultaneously? In that case, I will get a flux vector is equal to Ex times Jx this is equal to minus d into Ex dc by dx plus Ey So, the point I am trying to get at is that in this particular case, since we are dealing with variations in all three directions simultaneously, we will get partial derivatives in the equations of motion, and those equations of motion will therefore become partial differential equations. Okay. So, locally we will do a balance at a given point in the equipment, okay, and get a partial differential equation which tells us how the variation in temperature at that point is related to its gradients and so on around that point from a conservation condition as well as from a constitutive relation. Okay. So, this gives us the variation at a point. Now, we have to find the variation over the entire system, okay, and that is a process of integration. Okay. So, for example, if I had a curve in just one dimension f of x as a function of x, okay, the derivative at a point gives me only the variation of this function at that particular location. If I want the change in function across a distance x, I have to take the derivative and then integrate that over that two intervals. Okay. So, there are two processes here. One is formulating the conservation and constitutive relations themselves, which lead to partial differential equations, and the other is using that to solve the problem. Okay. So, these partial differential equations we will use in conjunction with what are called boundary conditions in order to solve the problem. So, the boundary conditions basically will tell us what is the concentration of the surface, what is the concentration far away, what is the density and velocity at the wall of the tube, and what is the pressure difference across the two ends. So, those conservation equations together with constitutive relations which give us partial differential equations with boundary conditions will be solved to get the variation across the entire system. In the case of linear ordinary differential equations, there is a simple way to solve it. Okay. You are guaranteed there is a solution and that is unique. In the case of partial differential equations, there are no recipes, no algorithmic ways of solving them. Okay. Solution of these is coupled with a physical understanding of the system. Okay. What we will do is we will look at various different regimes. One is where diffusion is dominant, the other is where convection is dominant. Try to simplify the problem to the extent possible, okay, and try to get a solution which captures the essence, okay, of the physical processes that are going on without trying to be exact or accurate. Okay. These partial differential equations can also be used in computers to get complete solutions, okay. But that is not our objective here. The formulation as well as the physical insight which will tell us physically how solutions change as different effects which balance each other become larger or smaller. Okay. How those balancing of those effects is related to the terms in the differential equations, that will be the objective of the present course. Okay. So, basically I will try to give you a physical connection between the equations themselves and the physical processes that are going on in the real system. Okay. Next lecture I will start off on diffusion. Okay. This is important because, as I said, there are two mechanisms, one is convection and one is diffusion. Okay. Convection is just transport due to the mean flow. Okay. Diffusion is what gives us the constitutive relations, okay, which tell us how the fluxes vary with changes in concentration and so on. Okay. These kinds of relations are diffusion relations. Okay. They tell us how various fields vary as you change various quantities. Okay. Next lecture we will get a physical understanding of what is exactly the meaning of diffusion, why diffusion happens, can I estimate what those diffusion coefficients are just from simple physical arguments. Okay. This will give us a deeper physical understanding of the diffusion process itself, okay, both in liquids and gases. Okay. Once we have done that, then we will use these balance conditions, okay, the balance of both mass, momentum and energy, in order to find out equations for variations in one direction and then solve them for those variations in that one direction. Okay. So, we will start on diffusion next class, okay, and we will go on to solving real problems after we get a brief overview of diffusion and the physical mechanisms therein. So, we will see you next time.